Okay, so now that you have experience programming in ROBOTC with our VEX kits, we need to talk a little bit about programming design using the software. We're going to be using behavior-based programming. And as it says here, behavior is anything that your robot does. So for example, if you wanted to turn on a single motor or servo, that's a behavior. There's three main types of behavior, and this is really where it's going to be super helpful to think in these terms. You've got your complex behaviors. This is the big overall thing. And this is where the robot's going to perform a complex task. So for example, automate fan control. That's the whole point of this exercise that maybe you're building your robot for, is automate some sort of fan control. So there's also simple behaviors. That's where the robot performs a simple task, and you got your basic behaviors. This is what a lot of people think of when they think of programming. These are the single commands to the robot. So the example here is start a motor. And the secret here is complex behaviors are broken down into simple behaviors, which are then broken down into basic behaviors. So a complex behavior is what it says. It's the task or the overall goal that the whole program is going to accomplish. So in this example, we have a fan that runs until somebody needs it to stop. There's a safety device warning light that turns on before a fan turns on, and another light indicates that a fan has stopped. So that's your complex behavior. That's the overall goal. It's what you want this thing to do. So you may have one or more complex behaviors, just like it says here. Pseudocode is going to be important for when you actually program. This whole process is programming, and it's not just typing in code. There's coding and then there's programming. And in this case, we're going to write some pseudocode in which you break down behaviors into individual actions. Okay, we're not really concerned about the syntax or what the actual commands are going to be in ROBOTC. We simply describe them in short phrases. So in this example, our pseudocode would be, we got to think like a robot. We want to turn a motor on for 3 seconds. We want it to follow a line until it runs into a wall. Okay, that's pseudocode, just what you want the robot to do. So our complex behaviors can be broken down into simple behaviors. And all we got to do is list the simple behaviors line by line in the correct sequence. So what's the order of events here? You want to describe the actions and the prompt for each action to start. For example, we have a warning light that turns on before the fan starts for 3 seconds. So we have before the fan starts is going to be like the timing and how long is it going to last and what's going to happen. Another example is a fan turns on, and then what does it do? Well, it runs until a button is pressed. And then you have a different light turns on for 3 seconds before the program stops. So now we have basic behaviors. This is where we take our simple behavior and we break it further down. This is written in terms of the input and output relative to the device. So here's our example here. We have a pseudocode of a simple behavior where line for line, what happens? We've got our program starts, our light number 1, which is in LED 1 port, turns on for 3 seconds. Then our fan, which is in motor port 1, turns on until a button, which is in bumper switch, it's called bumper switch, and it's in that port, is pressed. Then what happens? Our second light comes on, which is plugged into LED 2 port, and it turns on for 3 seconds, and then the program ends. One thing that's very important, as you saw in that last slide, was that you have to have those ports identified. And so make sure you understand which sensors are analog and which are digital. A thing that's going to be very helpful to you is have a planning diagram. So here you can see in this diagram here, we've got there's all these blanks. We have our analog inputs, our digital inputs, and our motor inputs on this side. And we would just make in the blanks, we would write down what is plugged in where. So when you open the sample program, that the PLTW template, you're going to enter an initial task description of the overall program goals in terms of complex behaviors. Okay, so you're going to want to start with those complex behaviors. Then you're going to write some pseudocode in terms of the basic behaviors. Okay, so what is the basic behaviors you want your robot to do? That's going to go in the pseudocode section of the PLTW ROBOTC program template. So here's an example here where we have our task description, and we have just written in plain English what we want the task to do, what we want the robot to do. And then we have our pseudocode, and as you can see, it's broken up, and this is the one from earlier. It's broken up into our little basic steps, our simple steps of that thinking like a robot now, and thinking all the little individual steps that need to happen. Okay, this is before. See down here, task main, all that is going to come later. That's our actual program. We'll get to that soon. But first, pseudocode. Writing the pseudocode is what's going to help you actually write the code. Okay, so now in order for your program to work, you got to make sure that everything is labeled correctly. So like it says here, you enter the labels for all the inputs and outputs in the motors and sensors setup window, and then change the drop down to identify. So in this case, if you actually plug a motor, a fan motor, into port 2 on the Cortex, then that's just going to be it's just one of the motors. Okay, we call it fan motor because why? It's a motor. We're going to hook it up to our fan. Okay, but it's just one of the motors, like you had hooked up to the wheels, those green wheels. Okay, then we pull down the drop-down menu and we identify it as the motor. Okay, there's nothing. We called it the fan motor. Okay, there's nothing like. It's just the motor that we're using to turn our fan. There's not a fan motor in the box. It's just that's what we're labeling it. Then it says use a program debugger. That's the thing where you go in and you've done this before, where you just enter values for the motor just to make sure that it's working. And it includes not just motors. Obviously, here in our example, we want to make sure that these sensors and whatnot actually work as well. And we would see that in the debugging screen. Okay, so here, we're going to ignore all this stuff up here. We're going to look at our actual code, and you can see it's a different color. Green means comment. The computer, the program, the Cortex does not read these comments when they're in green. So you'll see it down here as well. This task main is going to be the beginning of our code. You'll notice a few things we'll talk about in a second, but this is the basic setup for having a motor turn on for 5 seconds, a motor that's plugged into port 2. All right, so take a look at that. You can pause this if you need to. Okay, so let's take a look at some of the code here. This first part says displays configuration change from motor and sensor setup. This up here, what you're looking at, just like this little orange arrow says, is just, you don't probably ever need to worry about that. Don't touch that. That will write itself once you got your motors and sensors set up in that little window that you've used before. Down here, though, this is the main part of the programming. Okay, so we've got our main task here. It's called task. You have to actually write it just like this, task main, and I think it's there when you start, so you shouldn't have to change that. But it's exactly what it sounds like. It's the main task of the robot. So everything after that is going to be what the robot does. Okay. In fact, to make sure that the ROBOTC and the robot can read it, you're going to have your main task start in a curly bracket and end in a curly bracket. All the programming has to happen between those brackets, at least for the main task. Okay. Now there might be, later on we'll learn about like side tasks, I'll call them for now, but the main task is going to be inside these curly brackets, and we're going to use these curly brackets a lot. It's going to encapsulate different sections of our code. So right now, our whole entire main task is encapsulated within those brackets, those curly brackets, or braces as they're calling them here. So if we break down our actual code for a moment here, we've got our start motor task. What's happening is the right motor. That's what we called it. There's nothing called right motor in our sensors setup. We called it, or in this case, in the example, we called it right motor. Okay, it's plugged into port 2, but we labeled it as right motor. And what are we doing? We're turning on at power level 63, which is half power. It's a positive number, and so it's going to be going forward. Then what? Well, we have our little command called wait. And it's exactly what it sounds like. We cause the program to wait for 5.0 seconds. Then we stop the motor. So we've got two commands. We had start the motor, and now we have stop the motor. And what is it stopping? It stops the write motor, which we called write motor, which is plugged into port 2, but we told it earlier that, it's the thing that's plugged into port 2 is called write motor. We're calling it write motor. Okay, so the end result is that our write motor spins for 5.0 seconds. I'm going to point out right now that every line so far has ended with these semicolons. That is like the period at the end of a sentence for code, and for ROBOTC in this case. So if you forget that, that program won't work. Okay, so usually basic behaviors combine to create a complex behavior. If your basic behavior doesn't work, then nothing else is going to work. So if your complex behavior is not working, go back and look at your basic behaviors, and chances are you'll find a problem there. So you want to create your code thinking of it as a series of small behaviors. And if you can do that, and if your pseudocode was good, that's going to be the success to writing, or that's going to be the key to writing successful code, is taking those small behaviors and writing the code for those small behaviors so that they add up to accomplish the main task. So one thing you're going to want to do is add comments as you build the code. Don't go back and edit later. That's a bad idea. Add the comments as you build the code. That way you will be able to keep track of what you're doing. So if you write turn LED on, and which LED is it going to turn on? It's going to turn on the one that we're calling LED 1. Okay, what's going to happen? Well, that turns LED 1 on. All right, I know it seems obvious, but it's not. What are you wanting this to do? Okay, and just make sure you comment to see these comments are your pseudocode. And if you've written good pseudocode, then the programming language should follow. Now we're testing these things, and so what we're going to do is we want to test these simple behaviors. So once we've established that this code works, the turn LED on, wait 3 seconds, turn it off, then what we can do is temporarily turn off these sections of code by using this comment stuff, these comment characters. Anything in between this and this is going to be comments. You can see it turn green in this example here. That means the computer won't read it. The Cortex won't read it. It's a comment now. And why would we want to do that? Because we're testing out lines 42 to 44. We want to make sure that works, and we don't want to have to wait 3 seconds every time while this LED turns on and off. So we're just testing this part right here, 42 to 43 and 44. Because and how do we do that? We commented out the lines 37 through 39. Okay, so this part is going to get tested. We're going to see if that works, and we'll go on from there. There's also a way to toggle it on and off. Honestly, I don't see the point in this, but you can if you're more comfortable with it. If you select all the text you want to comment out, you could. This is probably the most important thing or most useful thing is this Control Q. Rather than typing the comment code I was talking about in the previous slide, you can just select all the text, press Control Q, and it should toggle it off and on. Okay, so in the sample programs folder that I've shared with you, you should find the VEX 2.2 folder. Look for, you want natural language. It's been especially developed for us, for PLTW. It combines a whole bunch of common robot behaviors into a single command. Okay, so like you could tell the robot to go forward, and it will know what to do. All right, and then there's just a couple other things. It basically simplifies a lot of what we do, and it makes it, well, more natural. Okay, make sure that you go into the robot platform type. You choose VEX 2.0 Cortex, and you have natural language selected. So one thing worth looking into is this robot motion. It's basically all these little commands in here are things that would cause the entire robot to perform a behavior. They're kind of like pre-set up little codes that we can use. They might be useful, maybe not. I mean, you could use them if you don't want to, or if you want to. Okay, you'll also see some movement commands that are pre-done for us. One thing you'll find out is that sometimes things are going backwards. In that case, you just highlight this or you check that and it will reverse it. You can use negative numbers if you want to, but it has the same effect. Okay, this reverses the polarity though, like the entire time though. So any positive is going to become a negative, any negative will become a positive for the entire program. So there's just some commands here that are unique to our VEX hardware, the LEDs and the flashlights. So these are just unique to VEX. It's just worth noting. These commands are there for us. Just some other commands that are pre-written here. One thing to keep in mind is that the motor speed is affected by battery power. And that should be fairly obvious, but it's when you're in the middle of programming, sometimes the obvious stuff becomes less obvious. So they are going to rotate faster when using a fully charged battery, so make sure you use those. They will rotate slower when the battery is depleted. Just keep that in mind. The device is not going to move consistently as the power level drains in the battery. For the sensors, if something is pressed, it's 1, and if it's released, it's 0. Hopefully you've already seen that. Do make sure that there may be some bounce when you press a button. And so what's common to do and what might be helpful is to write a brief wait command to reduce that bounce effect. So what this means is that the program here will look for a bumper switch to be pushed. And then instead of immediately waiting for it to be pushed again, which it might sense as the bumper button is being released, it's going to wait 0.05 of a second before it starts looking for the bumper to be pressed again. Okay, so it's not a perfect. This is where the mechanical limitations of the equipment comes into play. So if you notice that happening a lot, this is a good idea to put in there regardless.